Okay, so we have seen how to construct a sequence of polynomials which are all orthogonal to each other with respect to some weight function in an interval, and we have seen how based on some very general arguments it's possible to show that all such sets of polynomials must satisfy a three-term recurrence relation. So in this lecture we will see a general differential equation that such orthogonal polynomials would satisfy, and the arguments involved are quite clever about how to arrive at such a differential equation. So it might be possible that some of you have already encountered such orthogonal polynomials actually starting from such a differential equation. So often in physics problems it's the differential equation which comes about from some real world application, and then we see that when we try to solve these differential equations using a power series approach like we did in some of the techniques we covered when we were discussing ODEs, and then the resulting solutions turn out to be some of these polynomials, and then we studied these polynomials. Often this is the route in which they were perhaps first studied, was also perhaps this is the route, and many discussions involving orthogonal polynomials also start from there. But in this the discussion we have followed has been to sort of look at it from an abstract perspective. So come up with a general approach to construct a set of polynomials, and then we're studying various general properties at this point. So in this lecture we will see how to make contact with the differential equations. Okay, so the trick is to consider this function fn of x. It looks somewhat like a contrived object, but you will see in some time why this turns out to be a useful quantity to study. So what you do is you take your w, you take your s, and then multiply it by the derivative of this nth polynomial in your sequence, and then take the derivative of this object and then divide by w, right? So that's how this function fn of x is defined, right? So you will see in a moment that this is a very interesting object to study. It is a polynomial which we will argue. So okay, let's not get ahead of the argument. So you have this object, it's weird object, so let's just do some algebra on it. So we have we can always assign an index n to it because there is this index cn sitting on the right hand side. So now we will just work out what this is, right? So if you expand this, we have think of this w times s as just some one function, and then there's another function, so you're taking the derivative of product of two functions, and so you have 1 over w of x times the derivative of this product, and then you leave the other stuff as it is. You just leave d by dx of cn of x as it is, and then the second term comes about when you treat this w of x times s of x as a constant. You pull it out, and so the w will cancel, and then you're just left with s, and then when you take the derivative it becomes the second derivative with respect to cn, right? So with respect to x of the function cn of x. Now, but in fact this object here, we should be able to identify it, right? So from an earlier lecture you can go and recap that, is in fact nothing but the first of these polynomials, c1 of x. c naught of x is a trivial one. c1 of x is identified to be this complicated stuff, is actually nothing but the polynomial c1 of x. So we can go ahead and rewrite this complicated construction as in fact nothing but fn of x is c1 of x times the derivative of the nth polynomial cn of x plus s of x times the second derivative of this nth polynomial. Now from this relation we can actually immediately say that this fn of x must be a polynomial of degree n. Why is that? So you see cn of x is a polynomial of degree n. So if you take a derivative with respect to x, it's a polynomial of degree n minus 1, and then you are multiplying by c1 of x, which is a polynomial of degree 1. So necessarily the product of a degree 1 polynomial with a degree n minus 1 polynomial will give you a degree n polynomial. Now this is kind of inconsequential, but let's look at it. So if you take the second derivative of an nth degree polynomial, it's going to give you an n minus 2 degree polynomial. So now when you multiply by s of x, the best it can do is to increase the order of this polynomial by 2 more, right? So because s of x the three choices we have: x squared minus 1, which will make it degree n minus 2 times 2 plus 2, which will become n, or if s of x is chosen to be x, or if it is chosen to be 1, for sure the degree of this can never exceed n. So overall, this is indeed a polynomial because of the way in which we are tying together various polynomials, and s of x is also either 1 or x squared minus 1 or x, so that's also a polynomial. So indeed this overall object is a polynomial and it has degree n. So now we will argue that it's not just any arbitrary polynomial, but it's in fact a familiar polynomial. To see this, we will first show that in fact fn of x is orthogonal to all these ci of x, all these polynomials we have constructed, where I goes from 0 to n minus 1. To see this, you have to consider this integral. So integral from a to b dx, the weight function w of x comes in, then fn of x, cp of x, where p can take any of these integer values starting from 0 and all the way up to n minus 1, and also n. So p can in principle can also take the value n. So in order to evaluate this integral, or take it a step further, we will replace this fn of x by this first expression we had. We have this 1 over w times the derivative. So it's convenient to rewrite fn of x in this integral as 1 over x, 1 over w times this derivative, and this w will cancel with the w which is sitting here outside. So you are left with this integral from a to b dx, d by dx of this w times s times d by dx of cn of x. Then there is an overall cp of x which is sitting outside. And now we integrate this by parts. So d by dx, so you have u dv, so it's going to become uv. So the cp of x times ws d by dx, that's the boundary term from a to b, minus this stuff. But I mean, immediately we can argue that the boundary term has to go to 0 because of the manner in which we have chosen our w and s. W and s have been constructed explicitly in such a way that this product ws must be 0 at the boundaries. So since you have this exact product sitting here evaluated at a and b, at each of the boundaries it's going to 0, so the difference is also 0, and so we are left with just minus v du. So in this case, so u dv, so this is v, so this stuff comes in as it is without the derivative, and then you have to take a derivative of this, and there is an overall minus sign, right? So because you are doing u dv, that's uv minus v du, v is here, v du is here, and there's an overall minus sign. So this is just simply integration by parts, right? So far it's just some manipulation of this integral, and now comes a very clever argument. So if you look at this, if you observe this integral on the right hand side carefully, so you see that this is now symmetric in n and p. Although what the integral that we started with, you get an fn and you get a cp, but we have managed to show that this must be equal to this integral, where if I exchange n and p, I get back the same integral, right? And this is equal to another integral where apparently on the face of it it's not symmetric. But if this holds, and if I can exchange n and p in this integral, then I should be able to exchange n and p in the other integral as well. And this is a great simplification. So what we can argue is, in fact, integral a to b dx w of x fn of x cp of x is the same as integral a to b dx w of x fp of x cn of x. And this immediately leads to a very important consequence, right? So when p is less than n, right, so clearly the right hand side is 0, right? So if fp of x, we already argued, is a polynomial of degree p, right? So and if p is less than n, so we know that cn of x is a polynomial from our box of polynomials, and cn of x is constructed in such a way that it is orthogonal to every polynomial whose degree is less than n. And if fp is a polynomial of degree p and p is less than n, we can immediately say that this right hand side is 0, and therefore the left hand side is also 0, right? So we have managed to show that whenever p is less than n, in fact this integral is 0. Therefore, we have managed to show that fn of x is a polynomial of degree n, and fn of x is orthogonal to all Cp of x whenever p is less than n. So p can take values from 0 all the way up to n minus 1, and then it's 0. So the left hand side is 0. So, but what is such a set of polynomials? So we have managed to construct a sequence of polynomials fn of x which have degree n, and these polynomials are orthogonal to all Cp of x where p goes from 0 to n minus 1, right? So this is a familiar object. In fact, fn of x is nothing but Cn of x, except that you can have some arbitrary factor associated with it, right? So this is in fact how we constructed the polynomial Cn of x. They have to be polynomial of degree n and have to be orthogonal to all lower order polynomials in that set, and that's exactly what is happening here. Therefore, in fact, this complicated looking object fn of x, which we defined as 1 over w of x times d by dx of w times s times this derivative, is in fact nothing but Cn of x itself up to some arbitrary constant lambda. So in fact, this is the differential equation that we were looking for, right? So this is a linear second order homogeneous ordinary differential equation which, if solved, will actually recover for us the solutions that we started with, right? So this is often, like we said at the beginning, is in fact the starting point. We start with a differential equation of this kind, and then we try to find a power series solution for such a differential equation, and then we discover these polynomials. So, but in this lecture we have managed to go in the opposite direction and show how for the sequence of polynomials we have constructed, we can actually work out the differential equation using the weight function and this function s of x, and everything is nice combination. And then we have argued that if you just do this operation and then if you write it like this, this is the differential equation corresponding to the sequence of polynomials of interest. Okay, that's all for this lecture. Thank you.